Welcome to MSB lecture series on main group elements. In my previous lecture, I was discussing about group 15 elements. While discussing, I did mention that white phosphorus having 4 phosphorus atoms with each one having a pair of electrons can perform as a ligand, and of course, many metal complexes of white phosphine as such are known. A couple of examples I displayed in my previous lecture, and of course, I will be giving you more information about the utility of phosphines or phosphorus compounds as ligands before I conclude the chemistry of group 15 elements. So, let me continue on phosphorus compounds, and phosphorus can also have ring, chain or cage structure. Anionic phosphorus rings, chains or clusters are also known. For example, P7 3 minus, P8 2 minus and P11 3 minus are some of the examples of anionic phosphorus cages, rings or chains. I will show you the structure of some of these in my next slide. You can see here P8 2 minus has this structure here, and also you can see where the negative charge is residing. This is P7 3 minus. Of course, basically what happens wherever the charge is there, essentially these phosphorus atoms are 2 coordinated, and P11 3 minus has a cage structure like this. And arsenic, antimony and bismuth occur predominantly as sulfides. These 3 elements essentially form layer structures very similar to that of black phosphorus, and arsenic vapor contains As4 molecules very similar to P4, and the unstable yellow form of solid arsenic probably also contains arsenic 4 units. At very low temperatures, antimony vapors contain molecular SbF4 units. At room temperature and pressure, arsenic, antimony and bismuth are essentially grey solids with lattice structures resembling that of black phosphorus, and arsenic, antimony and bismuth burn in air and combine with halogen. For example, and here M equals arsenic, antimony or bismuth. None of these elements reacts with aqueous alkali, but arsenic is attacked by fused sodium hydroxide to form sodium arsenite. So, this is essentially called sodium arsenite. Let us look into the compounds of group 15 elements. The group 15 elements form binary compounds on direct interaction with many elements, and the wide variety of possible oxidates of group 15 elements can be understood simply by looking into their electronic configuration, which is essentially NS2 NP3. One can anticipate, besides having +3 and +5 state, other oxidates also. However, compounds having other than +2 and +3 are very scarce. Nitrogen achieves oxygen state +5 only with more electronegative elements such as oxygen and fluorine. Of course, when we look into the electronegativity of all elements in the periodic table, nitrogen is the 4th most electronegative element. So, in order to make nitrogen compound exist in higher positive oxidates, only they have to be combined with either oxygen, fluorine or to an extent by chlorine. Oxygen state +5 is common for phosphorus, arsenic and antimony, but rare for bismuth, and most of the bis compounds have +3 as the most stable oxygen state. And of course, here inert pair effects dominates the chemistry of bismuth. As a result, +3 state is more stable for bismuth compounds. Since nitrogen is the fourth most electronegative element, it can also form compounds with negative oxygen state. For example, N3 minus ion, nitrate and ammonia, in which N is also in -3 state, are known, and nitrogen achieves positive oxygen states only in compounds with more electronegative elements such as oxygen and fluorine. As I mentioned, nitrogen does achieve the group oxygen state +5. Nitrogen forms simple binary compounds with other elements. They are classified as nitrates or azides. Nitrates are classified as saline, covalent or interstitial depending upon the other combining elements. The nitrates of metal can be prepared by direct interaction of the element with nitrogen or ammonia or by thermal decomposition of an amide. I will give you some methods of preparation of various nitrates. So, these are the few methods of preparation of nitrates. So, essentially saline nitrates contains nitrate ion, this is nitrate ion having 3 negative charges, and saline nitrates occur for lithium among the group 1 elements, and also for group 2 elements it has composition M3N2, whereas in case of group 1 essentially only lithium forms, others cannot form stable azides because of the larger size. You can see Li3N for group 1, whereas in case of group 2 elements it is the general formula can be written in this fashion because they are divalent in nature. So, in covalent nitrates, due to the presence of a covalent bond possess a wide range of properties depending on the element to which nitrogen is bonded. Some examples of covalent nitrates are essentially boron nitrate. So, boron nitrate has composition 1:1, and cyanogen, and also phosphorus nitride, and tetrasulfur nitride, and also disulfur dinitride. Okay. So, the largest category of nitrates consists of interstitial nitrates of the D block elements with formula Mn or M2N or M4N, that depends on the oxygen state of the metal, essentially D block element. Where the N occupies some or all the octahedral sites within the cubic or hexagonal close packed lattice of metal atoms, and transition metal nitrates are hard and inert in nature. Okay. So, they are essentially used as refractory materials and find applications as crucibles, high temperature reaction vessels and thermocouple sheaths. Nitrate ion is often found as a ligand in transition metal complexes as well. I am going to show one or two examples of metal complexes having nitrate as a ligand, as one of the ligand. Its high negative charge, small size and the ability to serve as a good pi donor as well as sigma donor means that it can stabilize metals in higher oxidation states, very similar to oxygen. The short coordinate bond between the ion and the metal atom is often represented as Mn. An example is the complex of this type. One can write like this, or one can also write something like this. Okay. So, one example is I will show you the structure of this compound here. You can see the structure of pentamine osmium nitrate complex. It has an octahedral geometry where one of the axial position is occupied by N, and essentially we have osmium to N triple bond here. Another important class of nitrogen compounds are essentially azides. Azides are toxic and unstable, and they are used as detonators in explosives. So, one should not confuse between azide and nitrate. So, the N3 single negative charge, whereas in case of nitrate we have one nitrogen with 3 negative charges. So, this is azide and this is nitrite. So, azides in which nitrogen is present as N3 minus may be synthesized by the oxidation of sodium amide with either NO3 minus ion or N2O at elevated temperature. For example, NH2 minus reacts with NO3 minus to give N3 minus. Or one can also start from N2O. In N3 minus, the average oxidation number of N is minus 1 by 3. The ion is N3 minus ion. So, this is for I am telling N3 minus ion. Okay. So, here each one is 3 minus only one, here 3 nitrogens are there. The oxidation number can be considered as minus 1 by 3 for each nitrogen. This azide ion is isoelectronic with N2O as well as CO2. Okay. And of course, azide is also a very good ligand towards transition metal ions. And heavy metal complexes or salts such as PbN3 twice, or HgN3 twice are shock sensitive detonators and decompose to produce the metal and nitrogen. Ionic azides such as NaN3, sodium azide, are thermodynamically unstable but kinetically inert. They can be handled at room temperature. They can also be used as source of azide for various other preparations such as organic azide and inorganic azides. Sodium azide is toxic and is used as a chemical preservative and in pest control, and when alkali metal azides are heated or detonated by impact, they explode, liberating nitrogen depending upon the quantity of metal azide involved in it. This reaction is used in the inflation of airbags in cars, in which the heating of the azide is by electrical means. Of course, I elaborated more about airbag and the utility of sodium azide in it for inflation. Besides azide, nitrogen compounds containing polynitrogen cations are also known. For example, N5 plus is synthesized from species containing N3 minus and N2F plus ions. For example, if we consider Na2F AsF6 in solution, when it is treated with HN3, it forms and HF formation will be there. Okay. You may be surprised to know the structure of N5 plus. This is how it looks like. So, overall charge will be plus okay. So, overall charge will be plus here, and here this angle is 111 degree and this distance is 129 picometer and this is 110 picometer, and whereas this angle is 166 degree. And similar to nitrogen, phosphorus forms compounds with almost all elements in the periodic table. Phosphates may be metal rich or phosphorus rich depending upon the composition, and that is based on the oxidation state of the metal or the other element with which phosphorus is combined. The phosphates of other elements can be prepared by heating the appropriate element with red phosphorus inert atmosphere. For example, here phosphorus we are considering is red phosphorus. So, there are many varieties of phosphates with formulas ranging from M4V to MP15. They include metal rich phosphates in which metal to phosphorus ratio is greater than 1, and monophosphates. So, one is with metal to phosphorus ratio greater than 1, and another class is metal to phosphorus ratio equals 1, and another set of compounds metal to phosphorus ratio greater than 1, they are essentially phosphorus rich phosphides, and here they are metal rich phosphides. The structures have a trigonal prismatic arrangement of 6, 7, 8, 9 metal ions around a phosphorus atom. Monophosphides essentially adopt a variety of structures depending on the relative size of other atoms. For example, aluminum phosphide adopts the zinc blende structure, tin phosphide adopts rock salt structure, and vanadium phosphide adopts the nickel arsenide structure, and phosphorus rich phosphides have lower melting points and are less stable than metal rich phosphides and also monophosphides. I will show you some of these phosphides in this slide. This is a tin phosphide. You can see here the ratio is 1:1, and here we have gallium phosphide, and you can see the red ones are gallium and gray ones are phosphorus, and this is indium phosphide. So, other hydrates of group 15 are essentially phosphines, formerly phosphane, are essentially the hydrates of group 15. We have ammonia, and of course, with phosphorus, that is they are called phosphines or phosphanes, having the formula pH3, and similarly we have arsine ASH3 and stibine SbH3, all are poisonous gases. The difficulty of oxidizing bismuth 3 to bismuth 5 by chlorine or bromine is an example of the inert pair effect. Essentially, if we take any of the trivalent bismuth compound, if we try to make an attempt to oxidize using chlorine or bromine, it is not easy because of the inert pair effect. The complete combustion of phosphorus yields phosphorus pentoxide, that is P4O10. Combustion in a limited supply of oxygen results in the formation of phosphorus 3 oxide or P4O6. Here phosphorus is in +3 state, and here phosphorus is in +5 state, and essentially that means combustion of white phosphorus in a limited supply of oxygen leads P4O6 phosphorus dioxide, whereas the complete combustion yields phosphorus pentoxide. Okay. So, this is how P4O6 looks here, and it is very easy to write the structure of P4O6 or P4O10 starting from P4. For example, we all know that this is how the structure of white phosphorus. So, one can simply like this here and then connect them with O. So, this is P4O6 partially oxidized one. You can see all phosphorus atoms are in trivalent state, and if excess of oxygen is there, this essentially forms P4O10. So, all phosphorus are going to +5 oxygen state. This is P4O10. Okay. So, indium and gallium arsenides and antimonides are essentially semiconductors. The compounds formed between metals and arsenic, antimony and bismuth can be prepared by direct reaction of the elements. For example, nickel, when it is treated with arsenic, it gives nickel arsenide. Gallium arsenide is the more important and is used to make devices such as integrated circuits, light emitting diodes and laser diodes. gallium arsenide. Its band gap is similar to that of silicon and larger than those of other group 13 and 15 semiconductor. As a result, gallium arsenide finds application and it is most sought after compared to others. Gallium arsenide integrated circuits are commonly used in mobile phones, satellite communications and some radar systems. So, now let me begin the discussion on hydrates of group 15 elements. All the group 15 elements form binary compounds with hydrogen, are toxic, having the composition like EH3. Okay. Nitrogen also forms a catenated hydrate besides NH3, N2H4, that is called hydrazine, you can see there. In addition to ammonia, nitrogen forms the hydrates N2H4 or diazine N2H2 and of course HN3, that is called hydrozoic acid. There should not be any confusion between ammonia NH3 and hydrozoic acid HN3. Ammonia is produced by the Haber's process. It is used to manufacture fertilizers and many other useful nitrogen containing chemicals. So, in this process, nitrogen and hydrogen combine directly at high temperature of 450 degree centigrade and high pressure of 100 atmosphere over a promoted iron catalyst to form ammonia. Okay. So, let me stop here and continue the discussion on hydrates of group 15 elements in my next lecture. Until then, have a pleasant reading of inorganic chemistry. Thank you.